Hello and welcome to today's conversation and discussion. My name is Gerald and I'm going to um, present to you a genetic survey finding from a rural African village. Our focus is on sickle cell anemia and malaria resistance and how allele frequencies have shifted due to environmental and demographic changes. And so we are going to look at a case overview of a population of 1,000 individuals, of which 4% have sickle cell anemia, represented by the small double S genotype, and the dominant cell allele, capital S, single S, which gives malaria resistance when combined together, making heterozygote, capital S and small s. And so this case is urgent because sickle cell anemia is a serious health burden, but the same allele also provides malaria resistance in carriers. And so migration from urban areas and rising malaria outbreaks may alter the genetic balance in this community. And so we are going to look at the historical data of which before mosquito migration, most individuals were capital S phenotype with a small proportion of carriers, which are the heterozygote, capital S and small s, and a few affected double S. This distribution provides our baseline for comparison. Here, we are going to see that in this equation, Q is the frequency of the recessive allele, small s, and P is the frequency of dominant allele, capital S, which is the dominant. These values are essential for Hardy-Weinberg calculations. And so the expected genotype frequency historical, we are going to see that the expected values assume Hardy-Weinberg equilibrium, meaning no evolution forces are active. So P squared into bracket 0.4845, excuse me, multiplied by 2, we get 0.714. And so the expected genotype is approximately 714. And so 2PQ is equals to 2 multiplied by, in the bracket, 0.845, also in the bracket, 0.155 is approximately 0.262. And so the expected heterozygotes are 262. And so 2 Q squared is equals to 0.024, and so the expected genotype is approximately 24. And so when we observe this timetable, we see the observed versus the expected, and so the observed double capital S is higher than the expected, while heterozygotes are fewer. This deviation suggests the population was not in Hardy-Weinberg equilibrium, likely due to selection pressures such as malaria. And so the observed capital S, double S, is 784, but the expected was 714. So the difference here is 9.8%. And so when we look at the heterozygotes, which is the capital S and the small s, we get that the observed is 192, the expected 262, difference is 26.7%. And then now when we see genotype, which is the observed is 24, expected is 24, and the difference is 0%. And so the current data here, we see that we have a sample of 100, and so out of the 100, the phenotype, we see, which is the capital SS is 64, and then we see the heterozygotes 30, and then we see the genotype 6. And so after migration, we see that malaria outbreak, we see a shift. The population of SS individuals has increased, showing a rise in recessive alleles, you can see. And so we see the recessive allele frequency increased from 0.155 to 0.245. This is a significant change in a short time, suggesting a strong evolution process at play. And what are the factors that are driving this change? This includes natural selection, which favors carriers, and so drift magnifies random changes in small populations, and gene flow introduces new alleles. Together, this process explains the observed shift. And what are the implications in the future? If Q continues to rise, sickle cell anemia cases will increase, straining healthcare. This heterozygote advantage may keep the allele in population, but the balance between malaria and the resistance and anemia risk is delicate. And so screening helps identifying carriers and affected individuals, which will reduce the malaria pressure and may also lessen the selective advantage of the heterozygote, which is capital S and small s. Larger breeding pools reduce random allele loss and also stabilize the allele frequencies. And in conclusion, this case demonstrates how evolutionary process acts in real time on human populations. And so public health strategies must integrate genetic and environmental realities to reduce disease burden. And so thank you so much for listening, and thank you for your time. On our last slide, we have our references for your future reference. Thank you so much for your time.